Hi, everyone. I'm Michael. I'm a research engineer at A16Z Crypto. And today I'll be talking about twist and shout, two new memory checking techniques authored by Srinath, Setty, and Justin Thaler, and how they fit into the Jolt roadmap. Oh, I realize I don't have the clicker. Okay.
You looking for the clicker? Yep, sorry. Table.
Some quick disclosures I'm obligated to include here. So what is Jolt? Fortunately, I was preceded by two other talks about zkVM, so I don't have to explain what that is. But what sets Jolt apart from its peers is that it's uniquely designed around sumcheck and lookup arguments, hence the backronym just one lookup table. This makes Jolt fast and relatively simple. It achieves state-of-the-art performance on CPU, and we have GPU acceleration in progress. And by minimizing the amount of low-level circuit code that's written, it makes it easier to audit and formally verify. So to make the simplicity point concrete, so this is basically all the verifier needs to know for the RISC-V less than instruction. Put another way, you can kind of think of this as the marginal audit surface of one instruction in Jolt. As you can see, it's just a handful of lines of regular Rust, no low-level circuitry required. Pictorially, this is roughly what the Jolt architecture looks like. So in the center, we have this small R1CS instance, which we prove using Spartan. And it serves as sort of the glue between the other components in Jolt. So we perform lookups into the bytecode, fetching each instruction based on the current program counter. We prove that using the lasso lookup argument currently. Similarly, we do instruction execution using lookups. And for read-write memory, we use the SPICE memory checking argument. So we use that for both registers and loads and stores to RAM. So now with twist and shout, this high-level architecture remains the same. We're just swapping out SPICE for twist as the memory checking argument, and lasso for shout as the lookup argument. In a bit more detail, what are twist and shout? So twist is a new read-write memory checking technique, while shout is a new read-only memory checking technique, or also known as a lookup argument. What makes them unique is that they don't require any permutation checks, so that means no grand products, no Reed-Solomon fingerprinting, no multi-set hashing required. All you need is some check. They use large but sparse polynomials, leveraging the fact that zeros are basically free for the prover as long as you use an elliptic curve-based commitment scheme. And this results in a faster prover and shorter proofs. We'll see some preliminary performance numbers in a later slide. At a more philosophical level, we see that this, with twist and shout, the prover cost profile kind of starts to converge towards more hardware-like performance characteristics. Specifically, we see that register accesses are faster to prove than RAM accesses, and that memory accesses are also faster with more memory locality. So now I'm going to give a very high-level sketch of what I see as the key insight of shout, the so-called method of one-hot addressing. So here we have a lookup table val. And for each access, we're going to represent the query as this one hot vector. So if 3 is the element being accessed, we have a 1 at that index and zeros everywhere else. Here RA stands for read address, RV stands for read value, which contains the lookup output at each step. So in the next step, we're accessing this 8, and then that 1, and then this one. And so with these RA and RV polynomials, we have this very nice sum-checkable expression here, which conceptually all it's saying is that the value read at time step t is given by the index that was accessed and the value of the lookup table at that index. And this is nice because RA is extremely efficient to commit to, given that it's all zeros and ones. In fact, you're only committing to 1 bit per cycle, basically. And also, this sum check is efficiently provable using some techniques described in the twist and shout paper. One caveat here is that we still need to prove that RA is indeed one hot, but for that, I'll again defer the details to the paper. Now, for a high-level sketch of twist, or rather the key insight of twist, which is the method of increments. So now instead of a static lookup table val, we have val which can be both read from and written to. So you can think of these as like 8 registers, initialized to all zeros here. And so every time we write to one of these registers, we're going to represent that as, instead of the write value, the increment, or delta. So here we're incrementing that register by 8. And then at the next cycle, we're going to increment this other register by 3. And then we're going to decrement that 8 by 2, giving us 6 in that register. And once again, this gives us a very nice sum check expression here. Conceptually, all this is saying is the value in register k at time step t is given by the sum of the increments for that register up to that time step t. So here, the LT polynomial is basically just the multilinear extension encoding that bit of pseudocode, which is if t prime is less than t, it's 1, otherwise it's 0. So for an example here, val of 5.2 is just the sum of those 2 increments. And similarly, val of 3.3 is the sum of those 3 increments. Right, so everyone's favorite topic, performance. So with the caveat that these numbers are based on some preliminary benchmarking in a still work in progress branch in the Jolt repo. Specifically, this branch does not yet integrate a polynomial commitment scheme, so we're just comparing sum checks to sum checks here. So sum checks before twist and shout and sum checks after twist and shout. So we can expect these numbers to shift around a little bit, but this is giving a rough idea of what to expect. In terms of proof size, we see that the Jolt proofs go from about 240 kilobytes down to 45 kilobytes, which is a 5.3x reduction. Prover time, the big headline number here is that instruction execution lookups get 7.3 times faster using shout instead of lasso. We see about 2.6x reduction in prover time for read-write memory and bytecode lookups. And sort of incidentally, we got a 2.2x speed up on Spartan. This is due to the fact that we were able to eliminate some of the R1CS inputs and constraints when moving to twist and shout. And the Jolt prover also uses about 3.3 times less memory at peak. And all this is with more optimizations still in progress. So what's next for Jolt after twist and shout? The main thing on our minds is streaming, which is a method of controlling prover memory usage without relying on snark recursion. So currently the Jolt prover uses memory that scales linearly with the length of the execution trace being proven. And other zkVMs, as you may have just seen in the previous talks, address this using continuations, which is basically breaking the trace into chunks or shards, proving each shard, and then recursively proving those. We're pursuing an alternative approach based on streaming algorithms. In the interest of time, I'm going to zoom through this a little bit. So this is roughly what continuations look like. And compare that to streaming, where we're going to make a sort of streaming pass over the execution trace, or rather multiple passes, generating the trace sort of on the fly, so that we only have to keep a small portion of the trace in memory at any given point. And there are some ways to speed this up. For example, we can take some checkpoints of the VM state on the first serial pass in generating the trace, and then in subsequent passes, we can generate the trace in parallel. So the benefits of the streaming approach, first and foremost, is simplicity and security. So no snark recursion means that there's no need to implement the verifier as a circuit. There's no need to introduce some sort of recursion VM or other proof system. And also, the security of snark recursion is thought to be on sort of shakier theoretical footing than non-recursive snarks. In terms of performance, we avoid the potentially costly snark recursion step. And also, specifically for twist and shout, we expect the prover to perform best on larger trace lengths. So we don't necessarily want to break the trace into small shards as we would do with continuations. And finally, while we're excited about this streaming approach, we acknowledge that there are certain benefits of the continuations approach as well. So it's important to note that streaming is also complementary with continuations. So eventually, we hope to get the best of both worlds. And that's all I have. Thank you, and happy to take questions.
And I've got the mic if anyone would like to ask Michael a question. Do we have any questions for Michael? All right.
In Lasso, it was required that it was MLE structured and decomposable. Do you know if in the new work it still needs both of those things?
Sorry, I missed part of that question.
Yeah. So in the original Lasso paper or the original Jolt paper, the arguments you were doing need to be MLE structured and also decomposable. If there weren't those two things, you couldn't use it anymore. With this newer work, do you know if you still need both of those things, or is it just one? Like, can you not have the decomposability property?
Yeah, so the lookup tables still need to be MLE structured. And there's also a notion of decomposability similar, but not exactly the same as Lasso. It's this something called prefix-suffix decomposability, which is described in, actually not the twist and shout paper, but a different paper proving CPU executions in small space.
Awesome. Do we have any more questions? One more.
You had mentioned there's some advantages to twist and shout if the system is instantiated over an elliptic curve-based commitment scheme. To what extent could you apply these to a non-homomorphic commitment scheme?
To a non-homomorphic commitment, yeah. Okay, so the main property out of elliptic curve-based commitment schemes that we need, well, one of the main properties is that zeros are free to commit to. So as you can see, like the RA polynomial here is mostly zeros. So that's the main one. In terms of homomorphism, I think you could get away without. We're actually not committing to that many polynomials total. I think it's something on the order of like 16 or 18. So you'd be paying like that constant factor of overhead on the proofs. But yeah, currently we're just looking at using elliptic curve-based commitment schemes.
Awesome. We have time for one more question if anyone else has a question. All right, let's give Michael a hand. Oh.